Hi, my name is Manish Gupta, and in this video, I'm going to talk about visual autoregressive modeling for image generation. This paper is a NeurIPS 2024 Best Paper Award winner. So let's get started and understand what is visual autoregressive modeling, right? So autoregressive modeling is very popular in the NLP world, where essentially you try to generate text token by token, and every token that is generated is conditioned on the previous tokens. Autoregressive transformer models, decoder-only transformer-based models are very popular, like GPT, Llama, Palm, etc. Right? One can also apply autoregressive modeling to images by trying to do image generation using the next image token prediction. So here, essentially, it's a sequential visual token generation setting where you basically generate tokens one by one in a raster scan order. So, left to right and then top to bottom in that senses. Right? However, this one, as we'll talk about in the next slide, this kind of next image token prediction is not the best way of doing autoregressive modeling for images. We'll talk about why this is not the best way, and empirically we will see what is a better way. A better way of doing this is basically visual autoregressive modeling. So in visual autoregressive modeling, the idea is to basically do coarse-to-fine next scale prediction that you see here, or next resolution prediction rather than next token prediction. Right? So visual autoregressive modeling makes GPT-style autoregressive models surpass diffusion transformers for image generation. For image generation, diffusion transformers have been very, very popular. But for the first time, an autoregressive model was able to generate images much better in quality, efficiency, and so on compared to diffusion transformers. So in visual autoregressive modeling, the idea is that multi-scale token maps, as you can see here in the picture above, are autoregressively generated from coarse to fine scales. That is from lower to higher resolutions with parallel token generation within each scale. So the idea is that, of course, all tokens which are generated in R3, for example, are dependent on all tokens which are in R2 and R1. But all tokens in R3 are independently generated of each other, which basically means that there is a nice mask that you apply such that R3 tokens basically depend on R2 and R1. But all tokens in R3 can be generated in parallel. Okay. Even in visual autoregressive transformers, the first step is still to encode an image into multi-scale token maps. So unlike in autoregressive transformers, the standard ones where you do not have multiple scales, here you actually have multiple scale token maps. On the next slide, I'll talk more details about this. For the autoregressive generation, as you can see, you basically start with the start token and you essentially generate a 1x1 token map. And then you progressively expand in resolution from 1x1 to larger scales and so on until you generate the largest scale possible. On the way, predict the higher resolution token maps conditioned on the previous ones. Right? So what is the architecture of visual autoregressive models? So first I'll talk about the typical autoregressive modeling for images, and then we'll talk about the weakness of vanilla autoregressive modeling, and then talk about visual autoregressive modeling of next scale prediction. So the typical autoregressive modeling for images can be expressed using a VQ, using a combination of VQ VAE, which is a quantized autoencoder model, followed by an autoregressive model, which basically takes the tokens encoded by the autoencoder model and does autoregressive modeling on top of them. Okay. So let me talk about how the autoencoder model works so as to identify these discrete tokens on top of which the autoregressive model is going to work and generate images. So the way it works is as follows. You basically start with an image I. Of course, you start with a very large set of images to train your autoencoder model. You start with an image IM, right? And then you use an encoder so as to generate feature maps F. These feature maps F are then quantized using a function Q in a space of Z different quantized vectors. So these Z or other vectors in this large embedding matrix Z, they all belong to a vocabulary of size V. So essentially, the way this is done is that you take the feature image F and then you divide it into different tiles of some fixed size. So let's say Fij is one of those tiles. You try to figure out the closest vector in your vector set Z, and then the discrete code associated with that closest vector is basically Qij. You take this Qij and you try to then do the lookup and essentially try to generate F hat, right, on the decoder side. So of course, Qijs are your latent quantized discrete codes in that senses. You try to generate the image again on the decoder side. I mean, after you've generated F, which is a feature map, you basically take this F and pass it to the decoder so as to generate a predicted image IM hat. Okay. Now, of course, for this autoencoder to work nicely, you try to minimize the reconstruction loss, IM minus IM hat. You also try to minimize the reconstruction loss of the latent image of the featured image, right? So basically F minus F hat. And then you also try to reduce the two losses, the perceptual loss of the related to the image, and then discriminative loss, like a style gain kind of discriminative loss for the generated image. After you have basically obtained this, you have figured out a way of tokenizing an image. So given an image, you can basically get discrete tokens Q out of them. Now, in autoregressive modeling, the idea is to basically take this grid of Q tokens and essentially define a one-dimensional order on top of them. So the previous autoregressive methods used to flatten this 2D grid of Q into a one-dimensional sequence by visiting the tiles in Q in a raster-scan order. However, these vanilla or previous autoregressive methods actually have various weaknesses, as I mentioned here. First, these quantized autoencoders, of course, encode bidirectional correlations. However, your autoregressive models only basically, assume or autoregressive models sort of make unidirectional dependency assumptions, which is basically contradictory to the bidirectional correlations which exist in the latent codes obtained using quantized autoencoders. Second, there's no bidirectional reasoning possible in an autoregressive setup. For example, can you predict the top part of an image given the bottom part? Well, that's not possible in a raster scan order. There is also the spatial relationship between tokens with their neighbors is also broken in this linear sequence order. And lastly, it is very inefficient. So for example, if there are totally n different tiles in an image, or other, if the height and the width both can be divided into n different parts, then you have the image is n cross n, so that's the n cross n tokens. And then when you do self-attention on top of them, that's very, very expensive, right? So essentially, overall, it leads to n raised to 6 kind of, order of n raised to 6 kind of latency in generating the overall images. Okay. So therefore, people do, therefore, in this paper, people have proposed visual autoregressive modeling, where the idea is that rather than doing next token prediction, you essentially do next scale prediction or next resolution prediction. It also operates in the same 2 stages. In stage 1, you try to essentially compute those multi-scale tokens or multi-scale discrete, tokens. And in stage 2, you're essentially going to use a visual autoencoder, visual autoregressive transformer model, so as to essentially, do autoregressive generation. Okay. So they propose a new multi-scale quantization autoencoder with a shared codebook Z across all the different scales. Now, of course, you have to basically quantize this image across multiple scales, starting from 1 cross 1 all the way to larger scales. However, they basically propose a multi-scale quantization autoencoder model which share the same vocabulary of discrete codes across these scales. There are more details in the paper about how this differs from the standard tokenization scheme of the VQVAEs. Right. In stage 2, you basically do autoregressive modeling using the next scale prediction. So you start with the start token, which is denoted with a S token here. And then you generate the first scale R1, all the tokens in the first scale, which is basically just 1 token. Then you essentially use this 1 token and you generate all the tokens in your next scale, which is R2. And then, which could be 4 tokens. And then you generate like 9 tokens in your next larger scale, R3, and so on. Now, cross entropy loss is used to capture, the loss between the predicted tokens and the actual tokens. Now, of course, this requires a special kind of attention mask, and therefore they propose a blockwise causal attention mask that ensures that each RK or each new resolution can only attend to the prefix R less than equal to K and does not really attend to other tokens at the same resolution. Okay. Now, how do these visual autoregression models perform? So as I mentioned earlier, this is the first time that autoregressive models could surpass diffusion models for image generation task. On the top right, you basically see on the x-axis inference time. On the y-axis, you can actually see FID or Fréchet inception distance. The lower, the better, right? And you can see the sizes of these models, and you see different families of models out there. DIT is the diffusion transformers, and you basically see different scales of those diffusion transformers. VAR, the visual autoregressive models which are proposed in this work, are also shown there. As you can observe, the visual autoregressive models are not just smaller, they also can help you obtain lower FID compared to diffusion transformers, and they are faster as well. They are faster as well, right? So in short, and these results are on ImageNet 256 cross 256 image generation task. So visual autoregression models with 2 billion parameters. The largest guy here is a 2 billion parameter model. Reaches an FID score of 1.73, which is basically much better than the DIT diffusion image transformer models with 3 billion or 7 billion parameters. The basic architecture is just a combination of the two stages or the two things, VQ-VAE autoencoder combined with decoder-only GPT-2 style transformers. Now, of course, for ImageNet, you basically need to do class-conditional image synthesis. So the way that is done is to basically use the class embedding rather than the start token here, or to initialize the start token. You basically use the class embedding essentially as the start token. Here you, of course, observe VR models of different sizes with the decoder models spanning depths of 16 to 30. So that's that. VR models, as can be observed, are way better than diffusion transformer models. In fact, diffusion transformers, remember, are very important because they are the basis of stable diffusion 3 and SORA, which are like state-of-the-art diffusion systems. But a VR model, visual autoregression model, is the right way of using autoregression for images and beats these diffusion transformer-based models also. The interesting part is that the authors also observed this nice scaling laws holding very good with the visual autoregressive models. So on the x-axis, you see the model size in billions of parameters. On the y-axis, you basically see token error rate. Of course, the smaller, the better. So what you can see is several models which have been trained to figure out the relationship between token error rate and the model size. And as you can observe, they follow a nice power law. They also observed that the model performs well on zero-shot generalization for tasks like image inpainting, outpainting, and class conditional editing. Right? So in short, in this video, I talked about visual autoregressive modeling, which basically does not believe in next token prediction as such in raster-scan order, but in next scale or next resolution prediction for image generation. It makes autoregressive models surpass very strong diffusion models in terms of all different aspects like image quality, in terms of inception score or Fréchet image distance and so on, diversity, data efficiency, and also inference speed. Lastly, it leads to a nice power law relationship between test performance and model parameters, or test performance and training compute, basically indicating that this is really the right way of using autoregressive models for image generation. That's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.